Bismillahir Rahmanir Rahim. Today we will discuss neurophysiology of nerve and muscle. Principles of neural and hormonal communication. As we know, there is two ways of communications in the body. Either neural, and this is our subject, and hormonal, which is regulated by hormones. To recall, all cells display membrane potential. All cells display membrane potential. Separation of charge across a membrane. Uneven distribution of sodium and potassium ions and large intracellular protein anions. We have two major regulatory systems of the body that ensure survival of the body, which are the nervous system, neural communication accomplished by nerve cells, or the endocrine system, where hormonal communication accomplished by hormones. When we are going to discuss neural communication, all we know that nerve and muscle are excitable tissues, as we said before. All nerve and muscles can undergo rapid changes in their membrane potentials, change their resting potentials into electrical signals. Neurons. Neurons gather and transmit information by responding to stimuli, sending electrochemical impulses, and releasing chemical messages or chemical neurotransmitters. The action potential. The action potential, when a certain threshold level is exceeded within the sodium ion influx, the depolarization of the membrane causes an action potential. We said before, there is a resting potential at approximately minus 70 millivolt. When there is a triggering stimulus which reached to threshold, the threshold level here is minus 50 or 55 millivolt. When a stimulus reaches this threshold level through influx of sodium ion, as we see in the figure, this causes the rising phase of the action potential, which is called depolarization, caused by sodium ion influx, and this is the start of the action potential. The depolarization of the membrane causes an action potential to quickly change from minus 80 millivolt or 70 up to positive 30 millivolt, and we must know the change of polarity from negative to positive. Here minus 70, the resting. Here is the threshold, minus 50. Here is the 0 millivolt. Then the depolarization starts to increase all over up to positive 30 millivolt. It is a monopolar electrical burst. A monopolar have one direction that is immediately restored by the repolarization phase. This change will not travel along over to a non-end or a final. No, it will stop at positive 30 millivolt and repolarized أو بالمعنى العربي كده بيتعادل مرة تانية بعملية خروج البوتاسيوم ion. So when it reaches abruptly to positive 30, it will descend again down, and this is called the falling phase caused by potassium ion efflux. The sodium ion influx, as we said, in a positive influx, and there is a falling phase by potassium ion efflux. It is a monopolar electrical burst that is immediately restored by the repolarization phase and followed by an after hyperpolarization. Here it will reach threshold and descend down. The descending down this area is called hyperpolarization period of the membrane. Starting from the motor end plates, the action potential spreads along the muscle fiber in both directions and inside the muscle fiber through a tubular system. Hyperpolarization then ascend again to the resting potential. The excitation leads to the release of calcium ions in the intracellular space. This is inside the muscle. Linked chemical process. This is an electromechanical coupling. Finally produce a shortening of the contractile elements of the muscle cell. This is what occurs when there is excitation of a muscle membrane. While if it is in the nerve, there is an action potential propagation. This model linking excitation and contraction represents a highly correlated relationship. Although weak excitation can exist that don't result in contraction. If the excitation doesn't reach to the threshold, it will not result in contraction. From a practical point of view, one can assume that in a healthy muscle, any form of muscle contraction is accompanied by the described mechanism. لو شفنا أي شكل للمسل contraction لازم نتوقع إن هو مصاحب بالتغييرات اللي احنا قلناها ديت. Neural communication. Membrane electrical states. When we come to neural communication, and this occurs through neurons or nerve cells, we have different membrane electrical states. As we said, number one is polarization, in which in a state when the membrane potential is other than 0 millivolt. In a state when the membrane potential is other than 0 millivolt, this is called polarization. Depolarization, membrane becomes less polarized than at resting potential. Depolarization means the membrane becomes less polarized than at resting potential. Repolarization, membrane returns to resting potential after having been depolarized. يبقى repolarization تعرفها membrane returns to resting potential after having been depolarized. Hyperpolarization, membrane becomes more polarized. Hyper means more, becomes more polarized than at resting potential. This is the state of resting membrane potential. If we conduct here a voltmeter, which is a measuring device for the voltage. If we connect both ends, the negative ends with the negative area and the positive with the positive, we will find a current flow which equals minus 70 millivolt. This is the inside the cell membrane and this is the outside. And we said in the last lecture that the inside is negative in relation to the outside. And we said also inside the cell there is sodium ion, potassium ion, chloride ion, and a negative protein anions, which have a large size. And this is the main cause of the negativity of inside the cell membrane, of the inside of the cell membrane. On the left we see the intracellular fluid, and on the right the interstitial fluid or extracellular fluid. And we here see pores which is permeable to potassium ion, and to certain extent to chloride ion. This is the membrane pores. The intercellular fluid contains negative protein anions, sodium ion, chloride ion, HCO3 negative, and potassium positive. Here is the concentration of each. As we see, the potassium ion has a large concentration. The negative protein anions have a large concentration. Sodium, chloride ion, and HCO3. This is the representation inside the intracellular fluid. And here in the interstitial fluid we find sodium ion with large amounts, chloride ion with large amounts, HCO3 large amounts but not reaching the sodium or chloride, and potassium ion with a small amount. The exchange which occur between the intercellular fluid and extracellular fluid, potassium will go out, making inside is negative at 90 millivolt, active influx of potassium ion, and active efflux of sodium ion. This is called potassium sodium ion pump. Types of changes in membrane potential. As we said before, the resting is minus 70 millivolt. Then an area of depolarization, which means decrease in potential, membrane less negative. Then repolarization, return to resting potential after depolarization. Then hyperpolarization, increase in potential, membrane more negative, and then return to the resting potential. Two kinds of potential changes occur: graded potential and action potential. The two types of potential change, you must know that we have one called graded potential, which serve as short distance signals. Graded serves as short distance signals, and action potential, which serve as long distance signals. Here is the two types of neural communication. neurons communicate either by graded potential or action potential. Ion movement. Electrical signals produced by ion movement across a membrane. As we said before, specific carrier-mediated transport. Leak channels open all the time. Gated channels can open and close, regulating permeability. So we have leak channels which are open all the time, and gated channels which can open and close, and by this regulating permeability. These gated channels have many types, which are voltage gated channels, which opens by voltage change, chemically gated channels, which needs a chemical change to be opened, mechanically gated channels, which open by any mechanical changes, and thermally gated channels. So gated channels have many types, either voltage, chemically, mechanically, or thermally. For every type of stimulus, it has a certain voltage gate, a certain gated channel. How it is a current, so we have voltage. When it is a chemical neurotransmitter, we have chemically gated channels. When we have a mechanical deformation, we have a mechanical gated channels. When we have a thermal change, we have thermal gated channels. Here is the picture of a voltage gated potassium channels. The gate here is closed. This is the extracellular fluid, and this is the intercellular fluid, and here is a plasma membrane, closed at resting potential, delayed opening, triggered at threshold, remains closed to peak potential, minus 70 millivolt to positive 30 millivolt. It opens in the peak, which is positive 30 millivolt. Delayed opening, triggered at threshold, from peak potential through after hyperpolarization from positive 30 millivolt to down to minus 80 millivolt. Here we see the retrograde and anterograde or normograde movement of transmitter vesicles through the neuron or nerve cell axon. Anterograde means movement of neurotransmitter vesicles or synaptic vesicles from the soma or the cell body down to the axon hillock. This area is called axon hillock, down toward the axon terminal or to the synapse area or synaptic area. This is called anterograde or normograde with the normal direction of function. Here is the return of the synaptic vesicles after its breakdown in the synapse or the synaptic cleft, and return toward the cell body from the synaptic terminal to the cell body, and this is called retrograde movement. Graded potential. It's just a local change in membrane potential, occur in varying grades or degrees of magnitude or strength, from minus 70 millivolt to minus 60 millivolt is a 10 millivolt graded potential. If it occurs from minus 70 millivolt up to minus 60 millivolt, it is called a 10 millivolt graded potential. The stronger the trigger, the larger the graded potential. Trigger will open an ion channel in a small specialized region of the membrane, usually voltage-gated sodium ion channel. And again, A graded potential is a local change in membrane potential. A local change in membrane potential. And as we see, it will not reach the action potential. If it is large enough, it will which reach a threshold, it will cause an action potential, and there the name is action potential. But it is less than threshold, it is called graded potential. Local changes in membrane potential occur in varying grades or degrees of magnitude or strength. From an example, from minus 70 millivolt up to minus 60 millivolt is a 10 millivolt graded potential. The stronger the trigger, the larger the graded potential. Trigger will open an ion channel in a small specialized region of the membrane, usually voltage-gated sodium ion channel. Here is the schematic figure for the current flow during a graded potential. This is the negative intracellular fluid, and this is the positive extracellular fluid, and this is a closed sodium ion channel. This is a portion of an excitable membrane or excitable cell. This is unbalanced charges distribution across the plasma membrane that are responsible for membrane potential in all cells. Number A, entire membrane at resting potential. All over the membrane is at resting potential. Triggering event opens ion channels, most commonly permitting net sodium ion entry. Here is negative and here is positive. Sodium ion is positive charged. Its channels open by the graded potential. It will enter inside the cell membrane. Here we have three parts of the membrane: inactive area at resting potential, and the active area depolarized, a graded potential by a graded potential, and the inactive area on the right, which is at resting potential. When the charge or the sodium ion enters inside, which is positively charged, inward movement of sodium ion depolarized membrane. This will make depolarization of the membrane, producing a graded potential. It will occur a graded potential. Current flows between the active and the adjacent inactive areas. As we see here, at this part of the membrane, the positivity will be moved, making the inside of the membrane positive, and the outside will be shortly negative. So it will travel to each side of the cell membrane. Here we have different areas. The area which is far away from the area of graded potential is still inactive area. Previously inactive area being depolarized, this area will start to depolarize, making it is positive and not negative, replaced by positive. Here the original area of the graded potential, and on the other side previously inactive area being depolarized, and away we have inactive area. Depolarization spreads by local current flow to adjacent inactive areas away from point of origin, and this is called a graded potential, which will travel to a short distance. Graded potential occurs in a small specialized region of excitable cell membranes. Magnitude of graded potential varies directly with the magnitude of the trigger event. This is a portion of excitable cell. Initial site of change of potential. loss of charge, here minus 55 millivolt, here it will be minus 60 millivolt, here it will be minus 65, here it will be minus 70 millivolt, and as we see, it will be demolished or disappear at all. Direction of current flow from initial site, right and left. Numbers refer to the local potential in millivolt at various points along the membrane. Current loss across the membrane. There is a current loss from minus 55 millivolt to minus 70 millivolt. Changes in membrane potential in millivolt relative to resting potential, magnitude of electrical signal, from 0, decremental spread of graded potential up to 15, initial active area, and then decremental spread of graded potential. So graded potential has a decremental spread. Decremental spread of graded potential, and this is a very important question. Decremental spread of graded potential. Graded potential, the stronger a triggering event, the larger the resultant graded potential. Graded potential spread by passive current flow. By passive, not active current flow. Graded potential spread by passive current flow. Graded potential die over short distances. Graded potentials die over short distances. Potassium ion leaks out of the membrane. Decremental gradually decreases. If strong enough, graded potentials trigger an action potential, as we said before. So we have two states, either graded potential or action potential. What will determine that? The amount of current change. If it reaches the threshold, it is enough to reach threshold and trigger an action potential, it will be causing an action potential. But if it is less than threshold, it will cause a graded potential, which is a passive current flow. Action potentials. It is a brief, rapid, large 100 millivolt change in membrane potential. Potential actually reverses. The potential actually reverses. Involves only a small portion of the total excitable cell membrane. It depends on all or nothing phenomena or law. Conduction without decrement. We said about graded potential, it is a decremental spread. Here, conduction occurs without decrement. In the action potential, conduction occurs actively without decrement. Types of change in membrane potential. Here is the area of entrance of sodium ion inside the cell and out flux of potassium ion out of the cell, and the rising and falling phases of the action potential. Action potential. When membrane reaches threshold potential, voltage gated sodium ion channels in the membrane undergo conformational changes. Flow of sodium ions into the intracellular fluid reverses the membrane potential from minus 70 millivolt to positive 30 millivolt. Flow of potassium ions into the extracellular fluid restores the membrane potential to the resting state. This is a comparison of graded potentials and action potentials, and this is an important question. Comparison of graded potentials and action potentials. You must know the differences. in the triggering events, in the ion movement producing change in potential, in the coding of magnitude of triggering event, in the duration, in the magnitude of potential change with distance from initial site, in the refractory period, in the summation, in the direction of potential change, in the location. 1, 2, 3, 4, 5, 6, 7, 8, 9 areas of difference. You must concentrate on them. Here, when we come to the triggering events in the graded potential, as we said, triggered by stimulus, by combination of neurotransmitter with receptor, or by inherent shifts in channel permeability. Here is the triggering for the graded potential. While in the action potential, triggered by depolarization to threshold, usually through passive spread of depolarization from adjacent area undergoing graded potential or action potential. Ion movement producing change in potential. The graded potential produced by net movement of sodium ion, potassium ion, chloride ion, or calcium ion across plasma membrane by various means, while in the action potential produced by sequential movement of sodium ion into and potassium out of cell through voltage gated channels. In the action potential, you must remember the voltage gated sodium and potassium ions, which is produced by sequential movement of sodium ion into and potassium out of the cell through voltage gated channels. In the action potential, we have voltage gated channels, while in the graded potential, we use leak channels or any sort which change the net movement of sodium, potassium, chloride, or calcium across plasma membrane by various means. Coding of magnitude of triggering event. In the graded potential, magnitude varies with magnitude of triggering event. This is an important point. The magnitude of triggering event in the graded potential changes with magnitude of the triggering event, while in the action potential, it depends on all or none membrane response. Magnitude of triggering event coded in frequency rather than amplitude of action potential. The triggering event, when its frequency is high and is able to reach to threshold, it will cause an action potential. If it is not able to reach threshold, it will not cause an action potential. This is the all or none membrane response, or all or none response. Duration varies with duration of triggering event. The duration of action potential is constant. Magnitude of potential change with distance from initial site. As we said, the graded potential is decremental conduction. Magnitude diminishes with distance from initial site, while in action potential propagated throughout membrane in undiminishing fashion. Propagated throughout membrane in undiminishing fashion. Self-generated in neighboring inactive areas of membrane. It is self-generated. Refractory period. The graded potential has non-refractory period, while the action potential has relative and absolute refractory periods. Summation. For the graded potential, we have temporal summation or spatial summation, and the action potential no summation occur. Direction of potential change can be depolarization or hyperpolarization. Action potential always depolarization and reversal of change. Location. The graded potential occurs in specialized regions of the membrane designed to respond to triggering event, while the action potential occurs in regions of membrane with abundance of voltage gated sodium channels. Propagation of the action potential. An increase in stimulus intensity beyond threshold will result in the rapid rise and fall of the potential, which is called action potential. Once the membrane has been depolarized above threshold, the generation of action potential is automatic and no longer controlled by the stimulus. Here is the picture of stages of action potential as we discussed before. The action potential depolarization caused by influx of sodium ion or another positive ion makes the membrane potential more positive. When the membrane potential reaches threshold, voltage-gated sodium ion channels open. After 1 millisecond, voltage-gated potassium ion channels open, polarizing the neuron again. Sodium-potassium pump helps restore neuron to its resting potential. Resting potential is polarized typically at minus 65 millivolt. Excitability changes during different phases of action potential. During excitation, before reaching firing level, excitability increased. Absolute refractory period means excitability is lost. Relative refractory period, excitability relatively increased but still below normal. Supernormal phase of excitability can be stimulated by subthreshold. Excitability below normal, this is called hyperpolarization. This is permeability changes and ion fluxes during an action potential. This is the resting membrane potential at minus 55 millivolt. This is the threshold. This is the resting at minus 70, sorry. The resting membrane potential is at minus 70 millivolt. Resting potential, all voltage gated channels closed. All voltage gated channels, this is sodium ion voltage gated channel and this is potassium ion voltage gated channels, all are open at the resting, which is minus 70 millivolt. The stimulus starts. Depolarizing triggering event will rise from minus 70 to minus 55 millivolt. When it succeeds to reach this level, this is the threshold level. Here, as we see, the voltage gated sodium ion open, allowing sodium ion to enter inside the cell. This is the intracellular fluid and this is extracellular fluid. Sodium ion channel opens and is activated. Activation gate opens and activation gates already open. So start of sodium ion influx causing sodium ion in a rising phase, as we see, up to positive 30 millivolt. This is the peak. In the peak, which is positive 30 millivolt, sodium ion channel will be closed. Sodium channel closes and is inactivated. And the start of potassium ion channel opens. Activation of gate opens. The potassium will go out of the cell, outflux of the cell, as we see, from the intracellular fluid to extracellular fluid, causing a falling phase. Potassium out, falling phase of action potential. Falling phase, this will reach the threshold level and exceeds the threshold to the resting minus 70 volt resting potential. Sodium ion channel reset to closed but capable of opening. Here, the sodium ion channel are able to be opened. And then this area of hyperpolarization, further outward movement of potassium through still opens potassium channel briefly, hyperpolarized membrane, which generates after hyperpolarization. Still, this channel is open, making autoflux of potassium, and this causes hyperpolarization. When it reaches the threshold level or resting potential, potassium ion activation gate closes and membrane returns to resting potential. Just reaching the resting potential, the potassium gated channel will close. Principles of action potential. We said the all or nothing principle. Action potentials occurs in all or none fashion depending on the strength of the stimulus. If the strength is enough to trigger an action potential and reaching to threshold, it will cause an action potential. If it will not, it may cause a graded potential. The refractory period, responsible for setting up limit on the frequency of action potential. Refractory periods. We have two refractory periods, either absolute refractory period or relative refractory period. Absolute refractory period, as we see, absolute refractory period due to inactivated sodium channels at the area of positive 30 millivolt at the peak of the action potential. Here, sodium ion channels are inactivated, preventing any another action potential to occur. While relative refractory period, as we see this area, all are relative refractory period due to continued outward diffusion of potassium ion. Due to outward diffusion, خروج البوتاسيوم ion from inside the cell to out, this causes a relative refractory period. And relative refractory period occurs when voltage-gated potassium channels are open, making it harder to depolarize to threshold. It harder to depolarize means it is not impossible. It is possible, but it is harder. While in absolute, it is impossible to the action potential or depolarization to occur. When we reach relative refractory period, it is harder. It is impossible. It is possible, but with a hard work or a harder to depolarize to threshold. Thank you. And here is my connection details. You have my email and my mobile number, and hope to hear from you for any question. Thank you.